Hello, uh, welcome. So we're going to be doing lead code 169, majority element. So you're given an array called nums of size n, and you're supposed to return the majority element. The majority element is the element that appears more than n over 2 times. You may assume that the majority element always exists in the array. So what this means is, right? Given an array of size n, let's say 1 1, let's use the examples that were given to us, right? 3 2 3, it has a length of 3, right? The majority element is the one that appears more than 3 divided by 2, which is 1.5, which gives us 1, which appears more than once, right? So the best way to illustrate this is to sort this. So that is 2 3 3. And you can see we have a majority element here, right? Let's look at another example, right? Let's look at another example. 2 2 1 1 1 2 2. The majority, in order to visualize this, right? The majority element here is 2, but in order to visualize this, let's sort this. 1 2 2 2 2. Right? You can clearly see that this is the majority element, right? Maybe I haven't, let me space them out better so that you can see that the 2 appears more. Let's add here another 2, right? So we'll do 1 1 1 2 2 2 2 2, right? You can see that this is the majority element. Not one that appears n over 2 times, but more than n over 2 times. So here, the solution to this problem, the first and intuitive solution, is to simply place them in a hash map, right? Place them in a hash map, and then return the number that has a value in the hash map, which is n greater than n over 2, right? So we can do it here. So the intuitive solution is we create a hash map, which will be, we'll call it store is equal to counter of nums, and then we iterate through the nums array and return the value that has appeared more than n over 2 times, right? And we're guaranteed to have this value, right? Because they said you may assume the majority element always exists in the array, right? So for num in nums, if store at num is greater than length of, let's call it check actually, let's call it check. Check is equal to length of nums divided by 2 is greater than check, then you return num as the majority element, right? So this should work. And voila, it works. So this takes, the issue with this is that it takes extra space, although it does it in linear time, right? Another solution would be to, let me see, since we noticed when we sorted it, right? When you sort it, the majority element, right, will be at n divided by 2, at the index n divided by 2, right? For example, let me show you. So this is another solution. It takes constant space, but it takes n log n time, right? So for example, 2 2 1 1 1 2 2, right? This is our array with a majority element. When we sort it in n log n time using quick sort with constant space, we get 1 1 1 2 2 2 2, right? And our majority element will always be at this position, right? It will always be at this position. Because what's the length of this? 1, 2, 3, 4, 5, 6, 7. It has a length of 7. 7 divided by 2 will give us 3. 0, 1, 2, 3. Okay, this position, right? So let's say, for example, majority element was, let's try to do it in a different way. Let's say majority element was 1, 1, 2, 2, 2, 1, 1, right? So let's sort this. In n log n time, we get 1, 1, 1, 1, 2, 2, 2. This has a length of 7. 7 divided by 2 gives us 3, right, when we truncate. So this will be 0, 1, 2, 3, right? So that's another way of getting finding the majority element. Second one, we sort, which will be nums.sort, and then we simply return nums at length of nums divided by 2, right? It takes constant space because we sorted in constant with constant space, but it takes n log n time, right? So they're saying, could you solve the problem in both linear time and constant space, right? So we've seen two solutions. One which takes n space, but in linear time, and one which takes constant space, but it has a higher runtime complexity, right? So we solve this by using what's called Boyer-Moore's algorithm. So linear time solution with a linear time solution with constant space, we use Boyer-Moore's algorithm. Boyer-Moore's voting algorithm. They have other algorithms, but this is the voting algorithm, right? And the way it works is, okay, so we're given an array 2, 2, 1, 1, 1, 2, 2, right? So we do it by having a count variable to count if we choose, we choose a certain, if we choose a certain number, right? We count the number of occurrences of that number, right? And let's call that number the candidate number. When do we choose the candidate number? When the count is 0, right? And we count the number of times we see this candidate number. We increment count, but if we see another number, we decrement count, right? And the point of that is that once count comes back to 0, we know that that number is not the majority element, right? And the majority element will be the number that still remains as the candidate, because every time the count goes back to 0, we reset the candidate to the current number we're at, right? And the reason this works is because of this. It's because they guaranteed us a majority element, right? So the Boyer-Moore's algorithm works because we're guaranteed that there's a majority element. So let's code it up, and then I'll rewrite it. We'll trace it, right, so that you can understand it better. So we create a count variable initialized to 0. So count is equal to 0. Then we create a candidate variable to store possible candidates of majority element, right? Majority element. So we iterate through the array nums, setting the candidate variable and incrementing the number of times we see it. If we see other variables, we decrement the count for our current candidate variable. And if count goes back to 0, we set a new candidate variable. We reset the candidate variable. If the array contains a candidate variable, we simply return the last candidate when the loop terminated. But we are guaranteed a candidate, a majority element in this question, right? So I'm trying to drill this into your head. So I've written all this, but I'm going to write the code and then we're going to run through the code with these two examples that we were given, right? So for num in nums, right, we set our candidate variable if count is at 0, right? So this will help us reset it when count goes back to 0. So we say if count is equal to 0, then our candidate variable will equal to num. Candidate is set to our current num value, right? Then we increment the count if we see our candidate, otherwise we decrement our count. So if candidate is equal to the num we're seeing, so candidate is equal to the num we're seeing, we increment the count plus equals 1. Increment the count. So count plus equals 1. Else, it's a new number. We decrement our count. So once this loop terminates, we simply return the candidate. Right? So let's see if this works. Oh, I forgot to candidate. Well, you can set it to 0 or none, whichever you want. Candidate. Where did I make a mistake? Candidate. Okay. And voila, it works. Right? So let me take out these so that we can have a less verbose amount of code when we're doing the trace, right? Okay, just taking out these. Okay, so yeah, that's good enough. So which one are we going to use? We'll use these two. So first one we'll use is 3, 2, 3, and the second one we'll use is 2, 2, 1, 1, 1, 2, 2. Okay, so time for the trace. Right? So we're going to use this one first, right? 3, 2, 3. So we have 3, 2, 3, right? So we are at this position in the code, we are at count, right? So we initialize our count variable with 0, and we initialize our candidate variable, which the candidate stores the possible value. So we'll start it out with none. You can start none or 0, right? Then now we're going to iterate through our nums, right? 0, 1, 2, right? So what is our num value, right? So for num in nums, what's our first num value? Our first num value is here. Num is 3. So then we check if count is equal to 0, we set our candidate to num. So our candidate becomes 3. Then we ask ourselves, is candidate equal to num? Yes, they are. They are equal to each other. They're equivalent. So we increment our count to 1. So we don't execute this code here. We come back here, and our nums, if you look in the drawing, our nums shifts to this position, right? So we come back into the code. If count is equal to 0, count is not equal to 0, it's 1, so we do not execute that. If candidate is equal to num, we increment count, otherwise we decrement it. So what is our num? Our num is 2, right? So our question is candidate equivalent to 2? No, it's not. We do not execute this code. Instead, we execute this code, right? So we decrement our count. Our count becomes 0. Then we come back all the way to nums, to the for loop. If you look in the code, the drawing, we are pushing our num to the next value. So our num becomes 3. We come down here in the code. If count is equal to 0, then we set our candidate to num. So our candidate becomes 3. Then if candidate is equivalent to num, our count is incremented to 1. Right? Then we come back here, and this terminates because we've run out of values. So we simply return our most recent candidate, which is 3. And indeed, when you look at this, 3 is the majority element, right? So that is going to be the first one that we do. Right? So let me just copy these here. I'll put them a bit higher and better written. So count candidate and then num. Right? So let me rewrite this so that it's clearer. So we have 2, 2, 1, 1, 1, 2, 2. Right? Push it a bit up there, and then we'll get rid of this. Oh, sorry. We'll get rid of these. This will be 0, 1, 2, 3, 4, 5, 6. All right. We have our candidate. This doesn't look good. Let me rewrite it properly. So we have here our candidate. So this is a simple problem. It's just that the Boyer-Morse makes it makes it tricky because this is an algorithm that some two smart mathematicians came up with, two smart math and computer science majors, professors came up with. So you just have to like memorize this and understand how it works in case you asked, right? So we're going to start by initializing our count to 0. So our count becomes 0. And then we initialize our candidate. You either can use none or 0, right? So none. Then for num in nums, so we're going to iterate through our array. So num is here. This is the array nums, right? So our num becomes 2, right? So if count is equal to 0, then we set our candidate, right? Because we set our candidate every time count is 0. So our candidate becomes, so we're now at this code here. If count is equal to 0, we set our candidate to num. So our candidate in the drawing becomes 2. So now we come here to check to whether we increment. So if candidate is equal to num, in the drawing you can see candidate is equal to our current value of num, we increment our count. So our count is now 1. Else we don't execute this code, obviously. We come back here and our num is now at this position, is this value here 2. So our num becomes in the drawing 2. Then in the code we come back here. If count is equal to 0, which it's not, so we don't execute this code. If candidate is equivalent to num, is candidate equivalent to num? Yes, it is. We increment our count and we do not execute this code. So our count is now 2. We come back here. Our num has moved from this position to this position. So we check, is our count equivalent to 2? No, it's not. So we do not execute this code. Then we come down to the code below. If candidate is equal to num, right? But remember our num has changed to 1. So our candidate, which is 2, is not equivalent to 1. So we decrement. If you look in the code, we decrement. So our count becomes 1, but our candidate remains 2, right? So we come back here, and in this code we come back to num. So our num is now at this position. So in the drawing you see we've shifted our num. So then we check the count. So if count is equal to 0, but our count is not 0, so we do not execute this code. Then if candidate is equivalent to num, which it is not, because our candidate is still 2, right? And it's not equivalent to num, which is, it's not equivalent to num, which is 1, right? We decrement our count. So our count becomes 0, right? So we come back up here. We push our num here, right? So if count is equivalent to 0, then we reset our candidate, right? So our candidate now becomes 1, and remember our num, we've changed it to 1. So we check if candidate is equivalent to num, which it is, we increment our count, right? Because this is equivalent. So increment our count, and we obviously do not decrement. So we come back up here. Our num is now 2. You can see in the drawing, it's now at this position. Our num is now 2. Is our count equivalent to 0? No, it's not. So our candidate remains 1. And then if candidate is equivalent to num, we increment, otherwise we decrement. They are not equal, so our count becomes 0, right? So I'm just going to push this a bit up here so that we can have more space, right? Okay. So our count is now 0, and our nums is pushed to the last position. So if count is equal to 0, our candidate becomes num. So what is our num? Our num is 2, so our candidate becomes 2. Is candidate equivalent to num in this code? Yes, it is. So our count is incremented to 1, and we do not execute this code. When we come back here, the for loop terminates because our num in the drawing, you can see, we jump out, right? So we simply return candidate. And what is candidate? It's 2. And that is our answer. And as you can see, once sorted, it's 1, 1, 1, 2, 2, 2, 2. You can see that our majority element is 2, this portion here. So that is the trace and explanation of the Boyer-Morse algorithm. This takes constant space and worst case n time. Actually, all the time n time, because it has to go through every value. So that is the solution, and thank you. Bye.